So today I want to do one more lecture on machine learning, especially on the more advanced machine learning. We call it deep learning, and the typical deep learning approach uses the model called neural networks. Okay, a lot of you already learned it and tried it, and probably seen or heard about this multiple times. It's definitely the most popular computer science algorithm being used in the past, 5, 10 years, especially in the past 5 years. Okay, whenever people talk about AI today, you should know that most of AI is a very broad term. Okay, has a lot of different technologies, and then machine learning is only one type of AI. And then within machine learning, the neural network and deep learning, that's basically the most advanced, the most powerful, machine learning approach. The ones we have covered over the past, 2 3 weeks using the machine learning library like sklearn. Those are also called machine learning, but those are more like a traditional machine learning. As you can see, as I explained some of the series, most of them are based on some of the mathematical, statistical models that you can clearly define a function, write a formula to do that calculation, from the mathematical way. But that's not the case if you use deep learning and neural networks. Okay, so today I will just give you a very simple overview on this one because deep learning is a pretty big topic, pretty advanced. And but this is not a machine learning course. And honestly, I don't think you need to know too much of the details. And a lot of times, especially when you're trying to build applications, a lot of time you're just using the existing models, especially the trained model to make predictions. But you just need to know how do you tune the parameters, how do you change the algorithm, add different layers. So today, I'll just give you a very quick high-level overview on how it works. Okay. So very quick recap, guys. This is what we covered last week. Okay. So we told you about machine learning. We told you about a simple language model, not large language model. And then especially we give you this example that we give you some kind of sentences, and then we break them down into the table, right? So the first half of the sentence will be the input sentence, and then we're going to try to predict the final words. And then, but then last week we're particularly talking about you cannot just throw a string like this to a sklearn model because everything needs to be numbered. It should be normalized. In other words, we call it vectorized. So we need to turn that into some kind of a standard format using numerical representations. So we spent a lot of time talking about this count vectorizer. If you remember, we look at all the words and vocabulary used in the data set and we give them an index. And all we do is simply count how many times per word being used in this sentence, and then we generate an array. So that way we will have a perfectly aligned a list of a list or 2D array to use for our training model. For the training model, we still use this SVM model. Okay, a very famous classification model in sklearn. And then we call the training or feed process. After that, you can make some predictions. And from the example last time, you can pretty much see that more or less you can predict some of the words, the last word based on a given sentence. Even if the sentence is not complete, you can still get some of the words. At least you start to see how that language model actually can be built. Okay, very simple, tiny example, but I think it shows really the idea very effectively. Okay, but obviously, if you start to play around with more of these examples, getting more data, and you start to see the accuracy start to get less and less accurate, especially when the example is getting more complicated, data set getting larger, right? So that's very expected because if you think about inventory when we use ChatGPT, the way ChatGPT works, the kind of answer they can handle, the way they form the conversation, that's so much more difficult than just predicting the last word, right? So you're not gonna train every single possibility a human being can type into a model and only predict the next word, something like this. There had to be a lot more complicated process to do the inference, to go from one sentence to another, and then somehow extract the keywords and then get a key idea or meaning, and then get all these results. Again, that part, I don't think human being can even explain how that works, okay? It's all trained by the very complicated algorithm. If the process is that complicated, you cannot just use math or statistics to model it. And that obviously not how it works. Even though a lot of the natural problem, natural science, you can abstract it in a mathematical or statistical way, but obviously not everything. So for example, a lot of how human body works, okay, you cannot really just model that as a mass. It's way more complicated than the clear mass formulas, right? So that's why if you are really trying to do more complicated, more powerful, and larger language model, and we cannot just use the sklearn library, and we need a more powerful weapon. Okay, so most of the large language model today has been trained using the neural networks model, or we call it deep learning model. Okay, so that's why we just want to give you a very short lecture today because I cannot really go too much deeper on this one. I've been using the neural network a lot, but I'm mostly just using the models and changing the algorithms, taking the existing library to make it work. But that's pretty much enough for most of the applications. Okay. So what is neural network model? Okay, my favorite example is this. Okay, so if you think about it's because before large language model, okay, AI has already been popular since I explained 2015, 2017. One of the most successful AI application is Tesla self-driving car. So I don't know how many of you actually have tried this. Actually, it works really well. Okay, it works super well in highway. Local is getting improved, step by step. Not bad. Now this is a demo, as you can see, they released back in 2016. Okay, in 2016 they can already do this. I'm gonna just play this video very quick. All right, so this is a kind of I think their internal demonstration. And this is the older model of Tesla, but this guy is not holding the steering wheel and just go. And then what they are trying to show you on the right hand side, you don't have this one in actual commercial car. This is their internal system. But then the really cool thing here you can see is using different cameras, they are recognizing all the different objects happening, whether it's a car, moving car, or it's a person, or it's a traffic sign, or it's lanes. And then they can differentiate what they are. And with that boxes, a very accurate box, they can then figure out a position. All right. And based on what they see, and then they start to make decisions, whether to stop, speed up, make turns. As you can see, even back in 2016, people can already deliver the algorithm like this. Yeah, so this is a very sophisticated. And then if you understand more about the whole driving control, automated driving, we actually got involved a little bit on the electrical car back in 2010. We actually did an example. Since then, there are already a lot of electrical system being used in the car, but nothing on at this AI level because traditionally most of the cars rely on sensors and radars. And even right now, some of the self-driving car come that they use the lidar, a very big kind of a radar system they put on top of the car, and they do the kind of scanning, try to figure out obstacles, objects around the car. And that approach is very accurate, but it doesn't, it's first of all, there's extra piece and cost you have to put on top of the car. Um, but also, it's not too intelligent, it actually sees the obstacles, but it doesn't differentiate stuff. It doesn't know whether it's a people, car, or maybe they can detect the metal, but they can't see that's a sign. What does it mean on the sign? So just using sensor is not going to be enough. That's why Tesla was very aggressive in self-driving, and they did not use too much sensors. Okay, if you look at some of their articles, their announcements, the algorithm getting so much more advanced that they actually use, I don't know exactly how much, but majority of the control system is done with software only, with the camera only. That's a huge advantage. All right. But anyway, if you see this video, okay, and if you look at the right-hand side, obviously this program to recognize all the object, that is the key, and that is AI. Okay, basically giving a image, giving a frame. Now you tell me what kind of object there are and where they are, right? So that's the question or problem they're trying to solve here using the AI algorithm. Okay, now a very simple demonstration is that think about the whole video. Okay, so they have all the different frames. Every frame is basically just an image. Okay, what the algorithm is trying to do is that given that input image, what are the objects there and where they are. Okay, so obviously the algorithm analyze all the pixels and trying to figure out and recognize the object. So in computer vision, this is called object recognition. Okay, so the input will be just pixels, a lot of pixels, and output will be the type of the object and then the position of the object. All right, so that's what's happening behind the scene. Now, since everyone here knows how to write a program, now I ask you to write a program like this, just to analyze this one image to figure out the cars, all of this. It won't be easy. Now, you understand the images are stored as a 2D arrays with all the integers representing all the pixels, the color values. Okay, that part, you can handle it. But then how do you do the scanning? How do you decide if this car and the cars have different shapes, different colors, different model, and have overlaps, and this program get very complicated very quickly. Okay, so let's not talk about this kind of example yet. I still like to go back to the simpler example. Okay, the most classical and simple example in this case is this image classification example on dog and cat. Okay, so this has been a very old problem being used by a lot of computer scientists, especially in the field of AI, that if I give you a picture of a dog or cat, how could you let the program to decide which type it is? For human being, it's a very simple task to finish, right? But for computer program, it's not that easy. Over the past years, okay, past decades, people have been working on this problem a lot. Probably around 70s, 80s, 90s, people already had solutions and they improved the solution. At that time, the accuracy was about like 70%, 70, 75%, which was pretty good. And later on, after 2010, when more and more people started to do AI machine learning, and people figured out the neural network, which was the old model, but because all the data set and the computational power we have today, they started to redo this problem, and all of a sudden people started seeing accuracies above 90% and 95%, and eventually it's pretty much 98, 99% right now. So today nobody talk about the cat and dog image classification example because this problem has been solved completely. It is pretty easy thing for computer to decide which one it is. All right. So, but theoretically, if you look at Tesla model, the self-driving to recognize all object, it's actually very similar to this dog and cat example. I give you a picture, you tell me what that is and where they are. All right. So if you want to do this kind of AI or machine learning, okay, since you already learned machine learning, you probably can imagine or design how the algorithm works. All right. So to make a program like this using machine learning, well, you need to have all the data sets. All right. So if you want a model to be very accurate, you want to make sure that the program model can include as many possibilities as you can. All right, whether it's coming from the parks, the forests, or zoos, or books, right? And now it's a real cat or dog image, you should actually provide those. And once you provide all of this, you also need to label them. Remember, we talk about supervised learning. So tell a computer what this is. All these images here are cats. So you need to tell the computers and then send them together and then in a certain specific format. We see this all as images, but for computers, it's all just numbers. In this case, it's not hard to turn the image into numbers because the image has been stored as numbers, as I mentioned. Mostly it's 2D array with the, depending on the size of the image, with the right dimension. And every single pixel is represented by a number that's indicating the color value, depending on the encoding you use for the color scheme. Right, so that part isn't hard, but then you're gonna throw all of these images and pixels into the arrays with the labels to the machine learning model, and you can use it still SVM, random forest, all of this, it still works. All right, so they do this very complex training. Now, this is the actual training they probably will use using neural networks. Okay, but we'll talk about this one a little bit later. But yeah, so they look at the pixel, they figure out some of the features, and then they map them, form some of the layers. And once they're done with the training, they have eventually a model they can use to make predictions. Now, in the future, if you give an input image, and they're going to throw that into a model, and this is what a model will look like if they use deep learning. Okay, it's basically a bunch of layers, and then they go from one layer to another layer. It's almost like input, generate output, that output becomes another input, and then eventually they decide the specific type. All right, so that's how you use the model to make predictions. Okay, so this whole process of a cat and dog is the same as we've been doing like the iris flower example last week. Okay, so I tell you what those flowers look like. I tell you the type. I use the SVM to classify them, train the model, and then you can apply that model with new inputs. All right. So, but in this case, if you look at the, demonstration of these models, obviously it doesn't look like a very straightforward math or statistical models. So they use layers. Okay. We call it neural networks. And then basic idea is that they're trying to simulate how the brain works. Um, I'm not a biology expert, but there are neurons, there's kind of a networks in our brain. It probably, from one neuron you receive something, it becomes sensitive, and then that triggers something else, and eventually your brain got a conclusion or a decision. Okay, so that's how it works. But it looks very simple, like they draw here as a layer, but the actual um, way to form this model is pretty complicated. All right. So anyway, so this is just a very simple introduction to neural network. Whenever we talk about deep learning, first examples you should think about are image classifications. Okay, because that's when people find out this model works really well, extremely well. Because previously the cat and dog example were only like 70 plus accuracy, and now they can get to almost 100%. Yeah, yeah. So Carter, yeah, that's a also a good example. Okay, so they used all uh, the the data set for the art. Okay, so are you talking more like a kind of like a fake art kind of examples? Yeah, yeah. No, obviously that there are also some of the images you can trick the computers. A very famous example in cybersecurity. Some of you probably done those kind of projects. Is the stop sign example, right? So think about Tesla's car, right? So they see a stop sign, and then they're gonna recognize the stop sign, the car will stop. But there are some hackers, okay, they attack the model. So what they do is something like this. So they put some stickers to modify the sign. And the human being, well, you don't mind, okay? You can still see this stop sign. Probably some guy just put some bad stuff there, okay? So you will still stop the car. But in certain cases, this is gonna fool the machine learning model that the model will think this is a speed limit. It's not a stop sign, so it will not stop. And there will be a lot of risks and security issues. So a lot of researchers have been doing this cybersecurity research related with self-driving, and most of the time they're targeting the computer vision component. Right. Okay, so just a very quick and high level overview. Okay, so but I want to show you a very cool tool I really like. Okay, I don't want to dive too much about the coding, and then this tool from Google is a very cool, actually very advanced thing that you can play around with yourself to do this kind of deep learning. Okay, so they can help you to classify images, audios, or even the posts. Okay, so we just started from images. Okay, so I'll just do the standard model. Now they actually build everything on the web. I think the training also happening on the web. They use the JavaScript model, they use the TensorFlow model. So very advanced. So this thing is very simple. I'm gonna do some quick tests here in my office. And then, so just like how we do our traditional machine learning. So you need to decide the model, the feature, what do you want to predict. So in this case, I want to predict different type of images. Okay. So first of all, I want to start. I have a coffee cup here. Okay. So I want to do the first objects coffee cup. Okay. But first of all, I need to provide some images. Now for those images, you could give some images, but they can also use the camera here. Okay, to do it. So let me actually use the camera here to collect some images. I got my Starbucks today. Okay, I'll just show the logo right here. Okay, and then all you need to do is hold and just record some photos. So I just got a copy here. So this is, oh, it's already 48 images. Okay, 50. I'll do a little bit more. Okay, so that's the first one. And then I will do the second one. Will be the second one. All right, so the second one, maybe I will get I'll get a book. Okay. So I got this book here, Coders at Work. Okay. Highly recommend it. There are two books. One is called Founders at Work, and the other one is Coders at Work. You can take a look. Basically, it's just kind of interview book. It's a little bit hard to read. It's all like interviews. I think it would be nice to have a YouTube video to watch, but this is the old book. You can take a look at. Okay, so Coders at Work. So this is the book. All right. So let's actually get some images here. So I'll hold the book here, and I'll also get around 50 images. Okay, so that should be good enough. And then maybe we just add one more type. Let me see what else I have in Office. All right. Oh, I'll do this holder here. So this is before the pandemic. One of our students, I forgot his name, okay, but he 3D print a phone case for me. Okay, this 3D printing, okay, pretty cool. Okay, so you can put your phone like this. All right, so very nice. And then he had to give it me as a gift. Okay, so this will be a phone holder. All right, so let me get more images. Some different images here, different angles. Okay, 50 plus. All right, so now we're done with the data set. Okay, so same thing as what we did before. Provide data and the labels, the target, and now we'll start the training. Okay, so we don't worry about the model. Now I already explained this is deep learning model neural networks. Okay, so you click on the training model, and now they start to get all of their data set, probably pre-processing the images, and then they start to do the training. And then this one actually is super fast. Okay, so it's actually 150 images. Okay, now the model is ready. Okay, you can start to test it. Right now, I don't have anything. So it's actually real time try to predict what that is. Right now it's predict coffee cup, but it's not certain. Okay, so if I really start to hold my phone case, okay, phone holder. Very quickly, guys, you see this one here, the phone holder is classified as the most possible choice with the highest confidence. If you do a Starbucks coffee and that coffee shop shows up 100%, okay, very accurate, okay, even you change the angle. Or where's my book? Book here. And now the book shows up. All right. So it's really accurate, okay? And you can probably even do a random image, for example, the Starbucks, okay? So if I do a Starbucks, even I do something from, online, maybe this one here. Okay, so I'll save the image. All right, so if I put that back here, instead of using camera, I'm gonna use a file, okay? So I'm gonna do this one here, the one I just downloaded, okay, this image. And now if I put it here, and it gave me a coffee cup. So this is not in my office. I'm not showing in the image, but they can still recognize it. All right. And then the cool thing is that it's 100% confident. It's not accuracy, it means confidence. Okay, so three types, which one the model thinks it belongs to.
Professor,
Yes.
you think you can hold up a different book and see what it says?
Probably. at the end, they don't know what this book is a book or something else. They basically just look at the colors. Okay,
Right.
let's see this one. All right, yeah, this is a little bit confused. Yeah, but they still see it as a book. I don't
Yeah.
know at the side because maybe I'm not in the picture. Yeah, but now you see if my face is here, maybe they recognize a cup. Yeah, I guess that's probably the reason. Okay, so yeah, so but they don't know whether it's a book or a cup. They just know the pixels, colors,
Hmm.
and features, right? Um, yeah. So anyways, that's why the again the data set is so important. The amount of data you provide is just important. Okay. Um, but think about if we ask you to write a program like this, um, it's so hard to even think about how do you do that on algorithm. Okay, you probably can see the color ratio, those, but very quickly you end up with having some other complicated scenarios that you didn't plan before. But now you just throw everything to this model, and the model will get everything for you. Okay, so that is deep learning. Okay, so you can play around with this one. Okay, this is called a teachable machine. It works. Most of the deep learning model works very well for, the images, audios, and also text. Okay, so that's why the large language model also use a lot of this. Okay, so I'm gonna stop this one here. And you can also export the model, okay, through this teachable machine. And then you can embed it into your mobile apps or some other application, even Raspberry Pi. So this is actually very cool. Now you don't have to write a single line of code. That's my favorite part. All right. So but yeah, so if you see the example, guys, again, what I was trying to let you think about is the algorithm. How do you write this code? Because previously I've been to keep telling you to design a table, right? A table with all the, target feature and also all the input feature. I keep asking you the target. In this case, the target is easy, okay? Whether it's a cup, it's a book, or it's a holder, right? But what about the input feature? Okay, how would you even design that? Okay, these are images. Uh, you don't need to worry about a vectorizer because basically they're all 2D array with all the numbers, and then you can even resize the images so that they can all be the same size. But then once you have all the number, what do you do with the input feature? How do you design the features? Can anyone give me some ideas? Think about it. You have an image. That's how the image is being stored, right? So yeah, so it's a simple image, and then they store all the numbers, but inside the number, they're just pixel values. Okay, well, let me see which one would be a good example for this. Yeah, I'm trying to get an image to show that. Okay, so yeah, this one might be a good example that, but this image is not good. Okay. Mm. All right. Yeah, surprisingly, I want to just find an image on the left and the arrays on the right. I can't even find that one. Okay, but it doesn't matter. You pretty much can see it that the uh the image. Okay, so it has a color. Every pixel has a color, and there's a number in it. So you basically just use a 2D array to handle it. Okay, so that's how you process it. But my question here, guys, is that you're given with all this image, the 2D array. Now, if you follow the machine learning model I told you last week, how would you define this feature? Okay, you can't just give me all the numbers here because that doesn't mean anything. You just throw me all the numbers. You might want to summarize it, right? So for example, we talk about the text. And if you only give me all the characters, it doesn't mean anything. But if you tell me every word, the frequency it shows up, the total count, and that start to have some meanings, right? So does anyone have any ideas how you design the features that we could use for this table? Again, the question is that if we gave you all the images, okay, for you to make a machine learning model, let's say SVM, and you take all the pixels. Emil, do you have any ideas?
Is it maybe something with just like classification or tagging or something? Like somehow identifying like a pattern or something in the pixels? I don't know.
Yeah, yes, you're absolutely right. So you want to turn the pixel into some kind of pattern, right? I kind of mentioned one example. No, maybe I can see, for example, how many pixels are red. Okay, so or how many pixels are green. That's gonna help me to decide if this is a Starbucks, right? So that could be one example or one pattern as you suggested, right? So I'll say green color percentage, right? So yeah, depending on the thing you want to classify, okay, you can always come up with all of this. Yeah, image hashes. Yeah, but you can't. My question was, Kayla, that you can't just directly throw everything to hash something, okay, to maybe get some meanings, right? So that's just like what I mentioned here, the green color stuff, okay, or other color, or how many like color being used, okay, is that very colorful, something like that, okay, and another maybe you figure out the lines and edges, okay, so then computer vision you can do something called edge detection. It's also pretty cool algorithm, very easy to implement. Okay, so you give an image, and then we can actually draw all the edges. Okay, to figure out the most important outlines, or maybe look at this and then figure out some kind of a features. Right. So anyway, so the reason this is so hard to think about is just because for images, okay, it's not like traffic data or iris flower is all fixed, very straightforward. This one has so many and so much variance. Okay, so it's very hard for us to define all these features clearly and implement every possible features. Yes, Danny, that's pretty much what I mean. Yeah. So yeah, figure out the patterns and the colors, and then later on the shape and combination, which color next to each other, right? So because that's how you differentiate those images. All right. But then my point is that defining a table like this will be way too difficult. Okay, it's almost impossible. All right, so that's why people never use this one to do image classification today. Okay, so they use this deep learning model. The good thing about deep learning model is that you do not actually have to think too much about those details. You don't have to think about this. Okay, we'll let the the neural network to figure out by itself. That's why this approach is so cool. All right, so now for neural networks, guys, basically the simple idea is that it simulates how the brain works. Okay, and but to really explain and explain why it works so well, I think it's still a very hard research question today. Okay, a lot of research being done trying to justify why this model works so well, but I don't think that one is a complete solve. So I'm not trying to explain this one or use slides to tell you. This is one of my favorite videos that I've been using. it does a very good job to explain the neural network because it has all these visualizations. So I want to play this one a little bit. Now, I don't know how well you're going to hear that. I'm going to send this video to you. You can watch on your own, especially the first 7 or 8 minutes. It's a long video, but I think I really want you to take a look at the first 7, 8 minutes. Just get some ideas. It does a very good job to visualize and to animate how the neural network works. Okay, they use a very simple and classic example to recognize the handwriting images. Okay, please you can play on your own. You can watch my screen. Either is fun. Okay, probably only the first 6, 7, or 8 minutes.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years, there's been sort of a boom in research towards these variants. But in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own. And I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels.
All right, guys. Yeah, I'll suggest you can definitely finish the rest of it, but I'm not gonna play this one in the class. But you have to say that this video does a really good job of animating stuff. Okay, because the part I really like is the one that they talk about. Okay, so eventually, right? So this part here, you can think about you have so many layers for input and output. Eventually, when you try to decide which number it is, you actually need to look at how many of those components are there, right? And then but then getting to know that little circle isn't easy. That's why around that 9-10 minutes videos they were talking about how do they analyze the pixel to recognize there's actually a line. It's a like area with all the pixels light up, right? So but then the question is that how many layers do we need, and how do we split the layers, how do we design, the parameters that they mentioned, all of those should be coming from the training process. So by providing all these sample images, so the training will figure out all the parameters, just like the parameters for very simple traffic example on MX plus B, right? So how do we figure out the M and MB? That's the problem the machine learning trying to solve. Okay, but in this case, I want you to visualize this one to understand it still uses math, all the parameters, but it's not a simple mathematical or statistical model. Okay, so they actually try to figure out the features, the correlations, and then they group them, and then they build the layers so that you can direct all the input number from one to another. So that's why all these things correspond to the input numbers. It works really well with the image data because image data has a lot of numbers together. Okay, so that's why a lot of image examples, audio or text, they use neural network like this. Okay, but once again, guys, this is just a very high level demonstration. And there are also a lot of different type of neural networks available, and they have different application areas. Okay, now what I want to show you next is actually a piece of code that does this one, and they use TensorFlow, some of the very famous libraries. But before that, now what I want you to understand today is that even though we say sklearn is a type of machine learning and neural network, deep learning is also a type of machine learning, but sometimes people will tell you they're different, okay? But you should know it's more of how you use the terms. But generally, if we say the regular or traditional machine learning, I would like to say traditional machine learning. It means that's sklearn. We've been learning over the past couple of weeks. Okay, you define the table, you specify the feature, you specify some kind of decision tree, and then you query, plan all of this, and then use the model or set data set to figure out the parameters. Where the deep learning, you don't have to do those feature extraction. That's why I was trying to ask you the question, how do you define the feature for the images? The answer is you don't need to worry too much about that. All you need to think about is how do you reasonably split this problem into different layers, how many layers, and how let the machine to figure out the correlation by itself. And then you can see the second approach is so much easier to decide compared with the first one, because the first one, you still have to use a computational or programming thinking to figure out the details, where the second one, you just leave all the hardware to the computer to figure out. That's also why the second one works well, because if you think about how our brain works, right? So every one of us can recognize cat and dog. But if I ask you to summarize, how do you decide that's a cat and dog? you're gonna answer, well, of course that is just a cat and dog. There's no reason, or because you probably cannot really figure out a reason because the brain actually take care of it, right? So that's why the second model actually works. Okay, it's really trying to simulate how the brain works in reality. Okay, so that's the fundamental difference between the two. It's more of thinking how it's like a black box. Okay, you worry about input and output. You gave the training data. Don't worry about how that black box works. It's almost similar to the large language model. Okay, the ChatGPT is so powerful. We don't want you to really understand every single detail or algorithm, but you need to understand how do you provide a good input to generate good output based on the problem you want to try to solve. Okay, so here is a coding example. So when you do the example with the deep learning, okay, you generally cannot do that with Replit. Okay, Replit is very convenient. I like it because save all the code. It just runs just very quickly. But a lot of the large language, the neural network model or deep learning model, they do need, whether it's GPU or they need some special libraries or need more spaces. So the Google Colab, okay, normally it's the best place to go with this kind of an environment. Okay, but you can also set up your own local Python environment. So here is one of the very good tutorials. Google has a lot of good tutorials, okay, because the TensorFlow is the most important neural network model being used everywhere. Okay, TensorFlow is developed by Google. A lot of other libraries are built on top of this. So they have a lot of good resources. Here, I just want to go through one example here about this convolutional neural network example. Convolutional neural network is one kind of neural network, one type of machine learning model. It's just like SVM, random forest, they're all different kind of classification algorithm. This is just one algorithm. This algorithm works really well to classify the images. Okay, here is a very short example that demonstrate how this works. Okay, here I just want to go through the code because whenever I go to the deep learning, there are too many things going on. Okay, the parameters, all of this, a lot of this, you have to have a lot of experience to decide which one to use. So that's why I just rather follow the sample code and reference code. Okay, so just go through this. What they do is that they're trying to classify this CFAR images. And if you look at this, it's basically a very classical data set that does provide you all this test images. So they have a total of 60,000 images, but they make it very small. Okay, 32 by 32 color images. And then they have how many types? They have only 10 types: airplane, automobile, bird, cat, all of this, dogs. Okay, but then every type they provide 6,000 images. So a large data set, just like this. Okay, they offer this data set for a lot of machine learning community to run the test to see if their algorithm is better. So this is an example they're being used. You can download the whole the data set from their website, but then if you go through this code here, they start to import TensorFlow. They also use something called a Keras. Okay, Keras is also another library. If you start to do more for machine learning or deep learning, you definitely need to use this library. So Keras is basically a simplified library that use TensorFlow. Okay, so it's kind of like a wrapper that makes the TensorFlow much easier to write. So they try to make the code very short. Okay, so anyway, so very often you will see TensorFlow, Keras, they work together. Okay, now they import all the libraries and they have this plot library to draw the graphs. And the first thing to do is they have to download all the images. Okay, they download that from the University of Toronto website with all this 60,000 images. All right, so color images, they download it, and then basically it's all like formatted in the 2D arrays, 32 by 32. They also provide you the class name. There are total 10 of classes, okay? And then what they do here is they want to test and then show you those images, what it looks like. All right, so basically all they do is for every type, they just pick one image and then just give you a sample. As you can see, this image are pretty small, 32 by 32 pixels, not a lot. But then they do provide a large number of different types of varieties, right? So I think every type you have 6,000 images. All right, so they know the types, sorry, the names, and then they know the images, and you can just, it's already been labeled. All right, once you all have all this input data sample, now you can start to build your model. Now in this case, we're building a neural networks. Now remember what the video mentioned, the neural network has a number of layers to decide different things, okay? So when you use those models, you have to design a network, okay? You need to, it's almost like you design your home, like our office network, how many routers, how many computer, you may have a firewall, something like that. It's very similar to that one. In this case, they put 1, 2, 3, 4, 5 layers, in their model. Okay, they have a convolutional layer, they have the pooling layer. Okay, so you can start to Google this mean. I would just tell you the very basic idea. The convolutional layer is basically trying to search for those features. Okay, given the image, I want to search for the important part of the images. Okay, basically like a feature searching. And the pooling layer is trying to organize it, trying to figure out the relationship, which features you collected are important, and how do you summarize this? Okay, but again, my explanation are very high level. You could, start to get more explanation or through the ChatGPT to give you a better explanation. But you put these layers one after another in a sequential model. So that's how you implement the thing you see in the video from one input to another output. That output become another input to the next layer. So that's how they form the layer, right? So if you run this, it's going to form and configure all the layers. Here to show you a summary of the layers. So you have 5 layers there, and they have already been configured with the input and output. There's some parameters here. I don't want to dive too much. Probably talk about the size of the layer and the input, the shape, and the next layer, what's the size. All right. And finally, they also add a dense layer on top of it. But basically, I think the dense layer is trying to simplify and then put everything together. Okay, again, that's a very high level explanation. Don't worry too much. But after that, you just finally have a dense layer to cover everything to make a complete neural network. Once everything is done, as you can see, the most important thing here, or something you already learned, is called model.fit. Okay, so this is exactly the same thing as you've been doing with sklearn. In this case, the process is much more complex. I'm going to start running it first. Okay, in this case, it takes all the 60,000 images and it takes this sequential neural network model you form with 5 layers, and they started the training. All this training process they're trying to do right now is basically what the video is trying to show you, to figure out all the layers and what are those weights, okay, you want to put for every node, so that when the numbers come in, they start to times those weights and add them together and decide what's going to happen for the next output or the next layer. All right, so normally this one deals with larger amount of data, a lot of pixels, so that's why this training process is going to take a lot longer. As you do the training, they also shows you the accuracy. Okay, as you can see, as you goes more and more, the accuracy got improved. All right, and finally, they just shows you the overall training result and accuracy. And basically, based on the training, you can then predict the label. That's what you saw when I showing the teachable machine. Okay, you show an image, they tell you which type, every type, what's the confidence value, which type they think that belongs to. All right, so I think that's all the training. And then finally, they just show you the results. Okay, so eventually, I think the accuracy is about 71% for this case. All right, so that's the model they designed. But then if you want to improve the result, you're probably going to change the layer, change the parameter, and then to make it better. Okay, it doesn't show you how to make a prediction. I'm not going to write a code because I got to figure out how do you take a sample input image, get into the transformer to make it the number, and then do this. But it's going to be model.predict. Okay, but most of the research, they're trying to show you all the results, like of their training results. But this one, I just want to explain what the code looks like to implement ideas shown in the video, as well as the teachable machine, what's going on behind the scene. All right. So as I mentioned, for all the deep learning model, there are plenty of courses you can take, okay, to dive into more on this one. But the purpose of the large language model we're learning is that you understand that when they train the GPT model or some other language model, they all use neural networks. Okay, the sklearn won't be enough. Okay, so for example, you want to see how that works, like here, we got a very simple like hollow example. Okay, so you could turn this into a neural network model. Okay, so please change the following example of training a simple language model using sklearn into using the neural network. Okay, I'm gonna put the code. Let's see what they can generate. All right. So they can actually see that we use SVM model, and then they want us to use the Keras and TensorFlow. Let's see if they can get us code. I think they can do this. It's not too difficult. So in the linear stacks layers, they still use our same input data. They still use the counter vectorizer, and then they form the input and output data. They do some processing. All right, so the most important thing is here. They form a sequential neural networks. They have 2 layers, compile and fit. And now you make a prediction, okay? I don't know if this is gonna work, okay, but let's give it a try. So I'm gonna go to Google Colab. All right, so just create a new one. Whenever you deal with TensorFlow, you probably want to use the Google Colab. Wait, this is the one to generate. We want to generate. All right, so let's see if this one even works. Okay. So it should automatically try to download all the libraries. It does the same thing except that it use a different machine learning model here. Cannot import. Yeah, I think. Okay, so let's try this. Okay. How to fix the error. Right, some libraries got changed. So they asked us to replace. All right, so some of the library got replaced. Okay, I'm gonna recopy this part. Okay, try this. All right, run it. Wait, this is still not working. Oh yeah, so because I think the library was there. Okay, so it's this one here. Get it wrong. That's why you just need the 2 categorical. All right. This is another thing. So sequential has nothing called a predict classes. Yes, so this one, should we just do predict? Okay, so let me just search just to be making sure, okay? Yeah, we just use a predict like this. All right, wow, this code isn't very good. So NumPy. I think some of the data structure is not right. Yeah, it got the results, but all right, so it looks like this part is a little bit more complicated. Let's just try to use this part and hopefully that gave us something. Okay, so the goal here is trying to show everyone how the neural networks are being used. Okay, so I'm gonna do this one. All right, so yeah, that works. So anyway, I don't want to dig too much about this part because you know the output feed the data structure, okay, it's being changed. Okay, so I haven't dig into too much whether it's dictionary or hash table or whatever, but this code looks exactly the same as before. The only thing difference is this. Okay, it uses neural network model right now. You got two simple layers and then you do the feed, where the old code we do with SVM. Okay, so the training process looks the same, and then also it does some of the vectorizer, and but then again, the professional large language model probably does more than this. So again, I don't want to dive too much more on the neural networks. Okay, that probably needs at least a couple of semesters to get all the major topics covered. But I just want to have you have a feeling on how this works, and then maybe another good exercise or assignment to try to train some models with the languages using both sklearn and the neural network model probably would be helpful for you to get some hands-on experiences. All right, yeah. So that's the main thing I want to cover today, guys. Any questions about deep learning or neural networks? All right. If not, okay, I'm gonna put the code and slides in the same Google Doc, and then please expect another assignment. Okay, so this week just try to use the both model we learned and to do a simple exercise. Okay, now from next time we're gonna move on to some more applications. So we're gonna see some of the maybe some open source large language model that we can use, and then after that we'll start to move on to the prompt engineering part. All right. Okay, guys. Well, thanks for coming, and I will see you guys next time.
Thank you, Professor.
All right. Thanks, guys.